Welcome, Nocturnal Minds, aboard. Your learning journey starts now. So, building on our previous discussion about scientific models and how they relate to observation, let's dive into a concept that seems straightforward but is actually quite rich: prediction. Think about this simple card game scenario. I pick a card, slap it down face down. Your job? Predict if it's a diamond. Now, the event happened in the past, right? Yet, we still say predict, not postdict. It's the act of stating something about an event, whether it's already occurred, happening now, or yet to come. In philosophy of science, though, we're less interested in your guesswork and more focused on what theories predict. Okay, so when a theory predicts something, what does that mean? Let's start with the strongest kind, deductive prediction. Imagine my theory says, I picked a card from a deck containing only 10 diamonds. What can you predict? Well, obviously the card is a diamond. The theory doesn't just suggest it, it entails it. It logically guarantees it. This kind of prediction is timeless. If the entailment holds true today, it held true yesterday, and it will hold true tomorrow. There's no uncertainty here. If the theory H entails the evidence E, then the probability of E given H is E. Simple, clean, certain. Now, life isn't always so certain. What if the theory is weaker? Say I tell you, out of 10 cards, 9 are diamonds, and I randomly picked one. Does the theory entail it's a diamond? No, but it does imply something about the probability. The chance it's a diamond is 9 out of 10. Here's where things get interesting. We usually think of predictions as statements about observable events. It will rain. This particle will decay. Probabilities themselves aren't directly observable. You can't look at the card and see the number 9/10 glowing on it. So when dealing with probabilistic theories, we shift our focus. Instead of asking, what did the theory predict? We ask, how well did the theory anticipate the outcome we actually observed? The strength of this anticipation is captured by the likelihood, P of E given H, the probability of the observed evidence E, according to the hypothesis H. Crucially, this is different from P of H given E, the probability of the hypothesis given the evidence, which is what Bayesians often calculate. Think of deductive prediction as just a special case where the likelihood is E by %. But wait, even in physics, the bedrock of exact science, sometimes pure deduction gets messy. Take Halley's Comet. Predicting its return based on its previous path was easy peasy. Anyone could extrapolate the orbit and say, yep, back around mid-1759. But Clairaut, the French astronomer, did something more impressive. He predicted it would return earlier, near the beginning of 1759. How? By meticulously calculating the gravitational nudges from Jupiter and Saturn. These calculations involved approximations, truncating infinite series. Strictly speaking, there was no strict deductive guarantee, nor was there a probability assigned by the theory itself. So, what is this? It's not purely deductive, nor is it probabilistic in the way we just discussed. Let's call it rule-governed prediction. It follows established mathematical rules, techniques that are considered objective and reliable, even if the derivation isn't a perfect logical chain. It's still objective but acknowledges the practical limitations of real-world calculations. So we have these different flavors of prediction. Why does this matter? Because prediction is deeply tied to confirmation, how well evidence supports a theory. A common idea championed by folks like Musgrave is that assessing confirmation boils down to seeing if a theory's predictions pan out. If they do, confirmation. If not, falsification. If confirmation hinges on prediction success, then any debate about confirmation automatically becomes a debate about prediction. And one major debate is whether confirmation is objective or subjective. Objectivists say the relationship between a theory and evidence is fixed, like a logical connection. Subjectivists argue it might depend on things like your degree of belief, maybe even when you form the hypothesis relative to the evidence. This timing business is key. Let's test this intuition. Imagine flipping 10 coins, getting some sequence, say, H, H, TH, TTTH. That's our evidence E. Now consider two scenarios. Scenario E, someone looks at the results. then claims their theory predicted exactly this sequence. Scenario R. Same person makes the same prediction, but announces it before seeing the flips. Assume the prediction is correct in both cases. Which scenario makes you believe the theory is better confirmed? Intuitively, scenario R, right? The prediction felt novel, unexpected. But the only difference we're told about is the timing of the announcement. Does this mean confirmation is subjective, dependent on history? Hold that thought. An objectivist would push back. They'd say, okay, the historical fact of when the prediction was made is irrelevant, but only if we know the full logical facts. In this example, we don't know the logical facts. The objectivist argues that the timing tells us something about the logical possibility of fudging. In scenario E, after seeing the data, could the theorists have tweaked their model slightly to make it fit the observed sequence? Absolutely. They could adjust parameters until it spits out HHTHTHHH. But in scenario R, making the prediction beforehand, fudging like that is impossible. The prediction wasn't shaped by the data. So, the difference in our belief about confirmation reflects an objective difference in the logical situation. One involves the potential for retroactive fitting, the other doesn't. Confirmation itself remains objective, but the conditions under which a prediction is made affect how we assess the logical link. To make this precise, let's use a simple example, a beam balance. You know, the old-school balance scale. We put an unknown mass theta on one side, fix it E unit away from the pivot, and slide a known Ichenko mass along the other side until it balances. The distance x of the Ichenko mass from the pivot gives us the unknown mass x equals theta. Let's treat this equation x equals theta plus the assumption that theta is positive as our hypothesis h. What predictions can we draw from h alone? Well, it predicts that x must be greater than ling. Beyond that, not much. It doesn't tell us what x will be in a specific experiment. Okay, let's run the experiment. We balance the unknown mass, and the Ichenko mass ends up at xc 3. Let's call this observation E. Now combine our original hypothesis, h theta, with this new piece of evidence, EEX, E 3. Logically, this means theta must equal 3. So, we now have a fitted hypothesis. Let's call it h prime, which is essentially x 3. This new hypothesis prime perfectly entails the data we observe E. It accommodates the data, but here's the rub, the prediction that led to E was trivial. H prime entails E, no matter what H was. This is a classic case of the irrelevant conjunction problem or tacking problem. Just because E confirms H prime, which it does, trivial, it doesn't mean E confirms the original broader hypothesis H. H didn't predict xe 3, it just allowed it. Accommodation is weak, but maybe there's more to it. What if we run the experiment again? Suppose we get xr 4. Our original hypothesis, hx theta, implies that xe should equal xr. Since they don't, h fails to accommodate the combined data and er. It also fails to predict the second result. Now, flip the coin. Suppose the second trial gives xr 3, matching the first. Now h accommodates the combined data, but it's more than just fitting. The two independent measure mix, E 3 and xr 3, both point to the same underlying value, theta 3. This agreement, this overdetermination, is stronger than mere accommodation. It suggests the hypothesis has a robustness. Another way to see it allows us to predict one measurement from the other. Knowing xe 3 and h, we can predict xr should also be 3, and indeed, it is. This cross-prediction power is a sign of a deeper connection. How do we measure this predictive power formally, especially for probabilistic models? When we fit a model H to data E, we get a specific version of the model. Let's call it H. This fitted model assigns probabilities to the data. The degree of accommodation, or fit, is simply the likelihood P of a given H. If we have multiple data points E through En, assuming independence, it's the product of their individual likelihoods. But remember the fudging problem. To get a truer measure of prediction, we use cross-validation. For each data point EI, We fit the model to all the other data points, shish minus, and then ask, how likely was EI given this model built without using EI? We multiply these leave one out likelihoods together. This avoids the double use trap and gives us a measure of how well the model generalizes, how well it predicts unseen data points based on the rest. This is closely related to statistical methods like Akaike Information Criterion, AIC. Why does this focus on single-point prediction and likelihood resonate so strongly, particularly within Bayesianism? Bayesians aim to evaluate a hypothesis H by its posterior probability given the evidence, E. Using Bayes' theorem P of H, given E equals P of H times P of E, given H, divided by P of E, the data enters primarily through the likelihood term, P of E, given H. Now, often H isn't just one point, but a whole family of possibilities, like different values of a parameter theta. So, the likelihood P of E given H is typically an average likelihood across all possible theta values, weighted by prior beliefs about those theta values. As data accumulates, this average tends to be dominated by the maximum likelihood value, the specific hypothesis H that fits the data best. This convergence makes the Bayesian approach look a lot like evaluating the model based on its ability to predict individual data points similar to that leave one out CV measure. But does this focus on single-point prediction capture everything? Does it overlook other ways a model can be successful, like the cross-prediction or over-determination we saw in the beam balance example? Let's try a more complex example to see if this holds. Imagine we have three objects, A, B, and C, and we weigh them individually and in pairs. 6 measurements total. Let's say we get x1 等于3, x2 等于4, x3 等于5, x4 等于7, x5 等于9, x6 等于8. First, consider the primitive model, CRIM. It just treats each measurement as independent, introducing 6 unknown masses. It explains the data, sure, but it doesn't make any predictions about relationships between the measurements. Now consider the Newtonian model, NEWT. It adds the law of composition of mass. LCM, the mass of a composite object, is the sum of its parts. With LCM, we only need 3 unknowns, M, B, M, C, and crucially, each parameter is determined by 2 independent measurements, AG. MA from XE and X4 等于 MA 加 MB. Intuitively, NEWT seems far better confirmed. It provides a unified explanation, captures a physical law, and makes successful cross-predictions, but what does the average likelihood say? If we add error terms to make these probabilistic models, NEWT logically entails prim NEWT is just prim plus the LCM. Popper pointed out a fundamental issue here. If A entails B, then the probability of a given E can never be greater than the probability of B given E, based purely on probability axioms. So no matter how you choose your initial priors, your starting beliefs about the parameter, the math won't allow the posterior probability of the more restrictive NUPT to exceed that of the less restrictive prim, simply because of entailment. The Bayesian response? Okay, let's redefine prim. Let's mean prim minus LCM, meaning we assert that LCM is false somewhere. Then, yes, you can choose priors to make P of node given E greater than P of prim minus LCM given E. But critics argue this is a sleight of hand. First, it changes the original comparison. Second, why would anyone rationally assign a higher prior probability to the highly specific nub compared to the vague prim minus LCM? Third, it ignores the clear objective logical relationship and the intuitive sense that NEWT is better supported by the data. Let's tweak the data slightly. Suppose we repeat the experiment many times, and for x6, the average is 8.001 instead of exactly 8. Suddenly, the model prim minus LCM, which allows for errors in LCM, might perform better on leave one out cross-validation. It's slightly better at predicting individual noisy data points. A strict Bayesian might conclude, aha, the data slightly favors prim minus LCM over NEWT, suggesting LCM might be systematically wrong. But is that the whole story? NEWT still successfully predicted relationships like MA plus MB equals MA plus B that prim was silent on. Ignoring this ignores valuable clues about how Newt approximates the truth, even if it's not perfectly true. Understanding these nuances, where a model succeeds and where it fails, is crucial for scientific progress. It's a heuristic guide for building better theories. So, wrapping up the prediction section, prediction isn't a simple black box. It ranges from deductive certainty to probabilistic likelihoods to rule-based approximations. The standard Bayesian approach, while powerful, tends to boil everything down to a single number, the average likelihood. This can obscure important distinctions, like the difference between merely fitting data and genuinely predicting relationships or cross-validating successfully. Looking at these finer-grained aspects of how a model interacts with evidence tells us more about its strengths, weaknesses, and potential paths for improvement. Now, let's shift gears to probability itself. Where did this idea come from? Its quantitative roots trace back to Pascal and Fermat around 1660, formalized by Huygens. Right from the start, it had two faces, describing frequencies in games of chance and representing degrees of belief or uncertainty. By the 17th century, it exploded in applications, demographics, law, even physical sciences. Key figures like Jacob Bernoulli tackled the law of large numbers and binomial distributions, while his cousin Daniel worked on expectation and errors. Thomas Bayes introduced the revolutionary idea of inverse probability, estimating causes from effects leading to Bayes' rule. Then Kolmogorov in the 20th century provided the rigorous axioms, separating the mathematical structure from its philosophical interpretations. The first major interpretation is the classical view championed by Laplace. Think of Laplace as the Newton of France. His view was rooted in determinism, but probability arose from our ignorance. He defined probability as the ratio of favorable cases to total possible cases, assuming all cases were equally likely. This principle of indifference or insufficient reason was key. He also developed inverse probability, famously deriving the rule P of H, given E, is proportional to P of H times P of E, given H. However, this classical view hits snags. How do you define equally possible cases for a biased coin? And Bertrand's paradox showed serious problems when dealing with continuous possibilities. It's elegant but limited. The frequency interpretation, popularized by von Mises and Reichenbach, takes a different tack. Probability isn't about belief, it's about long-run frequencies. The probability of an event A is the limit of its relative frequency, m sub n over n, as the number of trials n goes to infinity. Von Mises introduced the concept of a collective, an infinite sequence of observations with stable frequencies, characterized by randomness, meaning you can't reliably win money betting on subsequences. This is purely objective and empirical. A big challenge, it struggles with single-case probabilities. Reichenbach tried to bridge this by positing that past frequencies will continue into the future, but this requires defining a reference class for the event, which itself is tricky. Enter Karl Popper with the propensity interpretation. He wanted to solve the single-case problem, especially in quantum mechanics. Propensity says probability is an inherent tendency of a specific experimental setup to produce a certain outcome. Think of it like the streakiness of a basketball player, a propensity to make free throws. It's an objective property, maybe unobservable, associated with the setup itself. Popper distinguished between long-run propensity related to frequencies and single-case propensities. He stressed distinguishing propensity statements about potential outcomes from statistical statements about actual observed frequencies used to test the propensity. While it handles single cases, propensity faces its own issues like the reference class problem again, and struggles to interpret inverse probabilis. What's the propensity of a bolt to have come from machine A? The logical interpretation, championed by thinkers like Keynes, Carnap, and Wittgenstein, sees probability as a logical relation between propositions. It's not about the world's tendencies or frequencies, but about the logical connection between evidence and a hypothesis. It aims to provide a rational basis for degrees of belief. Carnap, in particular, developed inductive logic as an axiomatic system, defining measures of confirmation or logical probability. He believed there was a unique, correct probability assignment for a given set of evidence, derived through logical rules like exchangeability. He justified induction via an appeal to inductive intuition. Others like Jeffreys took a more constructivist approach within this logical framework. Finally, the subjective interpretation most closely associated with figures like Ramsey and De Finetti. Here, probability is simply your degree of belief in a proposition given what you know. Is a personal psychological state. How do we pin down this slippery notion? Ramsey and De Finetti proposed operational definitions, like betting odds. If you'd be willing to pay $1 to gain $5, if event A occurs, your degree of belief in A is 1/6. The key constraint is coherence. Your beliefs shouldn't lead you to accept a sure loss in bets. De Finetti's representation theorem showed that if your beliefs are coherent and exchangeable, they automatically follow the rules of probability and Bayesian updating. For De Finetti, the idea of a single objective probability is misguided. Instead, we should focus on refining our subjective judgments through calibration against reality. So, where does this leave us? The classical view, tied to determinism, is largely outdated. The logical view, with its heavy formalism, often feels alien to scientists. Frequency and propensity offer objectivity but stumble with single cases or face interpretive hurdles. Subjective probability has a clear role, especially in social sciences and personal decision-making. Perhaps the most fruitful path forward is pluralism. Recognizing that different situations and goals might call for different interpretations of probability rather than forcing all uses into one rigid mold. It's about choosing the right tool for the job. And that brings us to the end of this whirlwind tour, through prediction and probability. Hopefully, this gives you a richer appreciation for the complexities involved. The further reading list offers plenty more to explore if you're interested.